welcome you and appreciate your opportunity to let us show you America's next generation rocket factory. Our job is to oversee the work of the Boeing partners that are with us making the core stage and later the exploration upper stage. Although this is a massive manufacturing facility and we do a lot of the assembly here, it's still true that about 80% of the parts that go into this rocket come from all over the United States and various vendors.
The core stage is actually built here at the Michoud assembly facility. It's been designed in Huntsville, and so we get to see this part of the rocket go from design all the way through manufacturing till it rolls out the door to get ready to go to Stennis for test. And so we get the really fun part.
One thing of interest here at Michoud Assembly Facility is the fact that we use robots ubiquitously all through the factory. We also use a next generation transportation scheme where we actually pick up these tools and take them where the hardware is instead of pick the tools up and carry them around on cranes and dollies, etc. That is a lot more manufacturing friendly, and it also enables us to make more robust tools that give us tighter tolerances. They're terrifically accurate. We're talking about down to thousandths of an inch in accuracy, which is interesting because as you look at the tools, they sometimes are many stories tall, and yet the manufacturing tolerance is down in thousandths of an inch. We have some tooling that we call rotational assembly and transport tools, whose function is to cradle the hardware when it gets to be large enough to be tank-sized hardware and ensure that we don't ratchet a torque or a stress or strain into them that could potentially cause a flaw or a crack in the welds. So we can protect this one-of-a-kind golden egg, we call it, hardware.
So this is our vertical weld center, and it is a conventional friction stir weld machine. We actually added this high bay onto the facility back under the Ares program, but we were very fortunate with a few modifications use this same facility now for the core stage on SLS. And what happens here is we get what we call panels. So they're very large pieces of curved aluminum. They come in, they are welded on this machine together to form a barrel. And those barrels are what makes up the primary components of the core stage. And you get the two panels in there, so they're like this, and then the machine is going to make a vertical weld. And then you'll add another panel, and you'll make another vertical weld. And you'll do that all the way around until you get a barrel section. And then once the barrel's done, we lift it out of the tool. So for the forward skirt, both of the tanks, and the engine section, they start out here with panels and then form barrels, and then they go off to the other machines in the factory that marry those barrels and weld the two barrels together, or we'll weld a barrel and a ring together depending on which one it is. The SLS rocket is about the equivalent of a 38-story building.
So I'm standing in front of the Vertical Assembly Center, and the tool that you see behind me is the Vertical Assembly tool. It's the largest weld tool in the world. This tool is where we will friction stir weld our liquid hydrogen tanks, liquid oxygen tanks, engine sections, and forward skirts. The welding is self-reacting friction stir welding. So friction stir welding, where we don't induce actual fusion or flame or heat. Okay, we're actually plunging a weld pin between two different volumes, two panels, a ring, a dome, a barrel, where the pin plunges and actually fuses those two materials together. Hence the term friction stir.
And the reason we like friction stir welding so much is you get a lot better properties than you do with conventional welding, and you get a lot better quality.
We inspect our welds using phased array ultrasonic testing, what the old fusion welds where they would have used X-ray. We've welded over 70,000 inches of friction stir welding here on the program to date with 0 defects detected in our welds. So this machine is 170 feet tall. We only perform the actual welding at one level of the tool. The tool works really essentially like a reverse Pez dispenser. We load each piece down in the bottom and it raises up. The weld is completed, we raise it up again, load another piece in, and continue the process until we're completely elevated and the dome is welded to a tank, for example, and then we were able to move the tank out of the tool and move on to the next article. It is the heart of the SLS. These are our liquid fuel tanks, hydrogen and oxygen tanks needed to propel the first core stage. And it is 2 domes and 5 barrel sections. Each of those barrel sections is 27 feet tall. So you do the math and you can figure out how tall that tank's going to be.
The segment and ring tool is a tool that we use to fabricate all the rings used all throughout the structure of the core stage. And following the initial weld, we'll have to machine away about half the entire thickness of the ring to get to the close tolerances we need, because that thick of a friction stir weld can introduce residual stresses and strains in the metal that if we didn't remove them slowly and carefully, you would kind of potato chip this 27.5 foot diameter ring. When doing the final machining of a typical ring, anything as subtle as a fan house above us blowing cooled air down may change the local temperature of the part such that it will be out of tolerance. So we even have to be monitoring the temperature, and in some cases, based on the process, the humidity, down to fine degree adjustments to be sure that we don't produce discrepant hardware. We also do the inside tank cleaning by lifting these tanks, the LOX tank and the hydrogen tank, over a lip and put multi-inches in diameter pipes down that snap out and spray detergent and rinse cycles and whatnot. So it's literally the biggest dishwasher probably in the world. And then finally, in one of the bays, we use water to approximate the density of the liquid oxygen that will go in that tank to do what we call a proof test. So we'll fill that whole tank with water, and then in a standpipe about a foot in diameter and 100 feet tall, we fill it with water again to approximate the weight that would be the same as the G-forces on the launch pad as it launches. And that gives us a confidence that any potential flaw that might be in those welds we find before we ever go further in the processing. In the foreground is the weld confidence article engine section that we'll use to practice weld rings onto. In the background is a weld demo article where we did our first opportunity to weld a barrel to a barrel segment, and then also welded a ring to a barrel segment. As is typical, before they do any significant operation on the tool, they'll have a safety huddle, which is what we see here with all the folks lined up, talking through the steps they're about to perform, being sure everybody is comfortable with knowing what their part is of it, because particularly as you get higher and higher build level, you're looking at multi-millions of dollars of hardware we're lifting up and around. And even a subtle mistake can be catastrophic at this level.
When we start talking about putting the core stage together, the part we're doing now that we've been talking about, which is welding, is the simple part. We take this nice barrel section that'll have a ring welded on it, and then we start stuffing it with electronics, with main propulsion system parts, with more wiring than you can possibly imagine. And you have to figure out how to get all those people in there to be able to put all this stuff in there in such a way that it makes sense, that it moves efficiently, and that you don't screw up something while you're working on the next thing. Whenever we start showing people the models of what this thing looks like when it's all stuffed, it's just incredible. So we have a tank, we have an inner tank, we have a forward, we have to put them all together. And we do what we call a forward join and an aft join. So we put the forward skirt and the LOX tank together. And then for the aft part, we put the hydrogen tank and the engine section together. And then we do the final join, which is when we marry those pieces together. And all of that is done in the horizontal area. One of the big things that you have to plan for from the very beginning is how you're going to move this stuff around, because it's so big. But you have to, in the design process, make sure that you've encompassed all the loads it's going to see on the barge and with the waves, and everything it's going to see as it moves from point A to point B. The barge that will take it is a barge that we've used before, but we literally cut it up, stuck in new parts in the middle.
It made more sense to cut the external tank era Pegasus in half, add length to it, and upgrade its shipboard electronics than it would to have begun from a clean sheet of paper.
Oh, sure.
Then we take it out to the barge, and we take it from the barge to Stennis, where it gets offloaded for the big testing that goes on there. And we'll have a little refurbishment to do after the testing, make sure everything's good to go, and then it will go back on the barge and go to Kennedy.
You know, the enthusiasm of the workers is obvious, and we're still ramping up in the hiring pace for the folks that will be not yet hired, that will be finishing this rocket before we roll it to the launch pad.
SLS is going to take mankind out to deep space. Yes, America's building it. We're building it for the world.